All right, so we are going to be using Zoom here, and I'm going to upload it using Kaltura eventually to be able to go through the lesson that we covered today because we had a little bit of some issues. So the first section we're going to cover today is 7.3 area and the definite integral. 7.3 is all about approximations. What we're trying to do is we're going to approximate an integral or approximate area using one of three different methods. So, for some notation, this is the integral from a to b of f of x dx. This is going to be defined as the area of the region between the curve of f of x and the x-axis bounded by the vertical lines at a and b. So what we're really looking at is what we're showing in this graphic right here. So we have our function f of x, we have our lines of x equals a and x equals b. We're trying to find the shaded area. The shaded area is what we're going to call as our area. The area here is always going to be positive. Anytime we talk about area is always positive, whether we are talking about it above the x-axis or below the x-axis. So anytime we're talking about an area of a region, it's always going to be a positive value. So our technical definition here. The definite integral definition. Let f of x be defined on the interval from a to b. Then the integral from a to b is given by the integral from a to b of f of x dx is equal to the limit as n goes to infinity of the sum from I equals 1 up to n of f of x sub I times delta x. That value right there on the right-hand side, this piece right here is an approximation. We're going to approximate that integral from a to b of f of x dx by using that limit. In order to do this, our limit must exist. And in order to find delta x, we're going to define delta x as b minus a all divided by n. And xi is any x in the ith interval. So if we think about an interval from a to b, say we had x1, x2, x3, and any number of other x's, what we're talking about is we're looking for this interval x sub I. The interval here is actually from a to x1, or from x1 to x2, or x2 to x3, x3 to x4, etc. So in every case, that's what we're actually looking for here. So to solve the definite integral by the approximation method. So currently, we have to worry about the three different ways we can approximate something. The first way that we can approximate something is the left endpoint rule. What this means is that when we draw these, what we're going to call as rectangles, which we'll see on the next slide, that the left endpoint of our rectangle will touch the graph. Then we're going to look at the right endpoint where the right side touches the graph. And then finally, we'll look at the midpoint where the middle touches the graph. If we were to add up the area of every single one of these rectangles and multiply by our delta x value, so the distance between x1 and a, or x2 and x1, like we saw in the previous slide, then we would in turn get a approximation here. So, but the first one we're going to look at is the left endpoint rule. Keep in mind, like I just said, the left piece of our rectangles that we formed all are touching at the left-hand side. Now, the problem with this is, if you notice, we have all this white space area in each case. This would be an underestimation because we're missing some pieces of it. We're missing this shaded in area that I'm shading in right here. We're missing this from our estimation here. So it's not the best accuracy that we can have. Now, if we think about the right-hand rule, the right-hand rule touches at the right-hand side of each one of these intervals here. The problem is we've got these shaded pieces that I'm shading in here that are all above the x-axis. So we're taking into consideration area that's not under the curve, which is what our stuff is talking about. So therefore, this is an over estimation. By having this overestimation, it's going to give us a value that's too high. So we had our left endpoint that gave us a value too low. The right endpoint rule gives us something that's too high. So if we look at the next piece, which is our midpoint rule, notice that halfway in the middle on every single one of these rectangles, we cross the x-axis. By crossing or not the x-axis, we cross the rectangle. So by crossing it right in the middle, that does leave us a little bit that's underneath, but we also have a little bit that's over. These are very, 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 very close to each other. So this is our best approximation. We're going to end up using all of these types of approximations, but we have to make sure that we understand and see what is going to be the best one in each case. All right, so these are the same PowerPoints that we've already seen. So all these examples were on clicks in my other one. But here everything is worked out. So for the function f of x equals 3x plus 2, we have this interval from 1 to 5, which is also the interval from a to b, and we're told n is equal to 4. So if we remember, delta x is equal to b minus a all divided by n. By using this value right here, we can in turn see that delta x is equal to 5 minus 1 over 4, which is 4 over 4, which is 1. Now, in this example, I did use a table. I like to more use a number line. So by using a number line, I'm going to create a number line from 1 to 5. It says n equals 4, so I need 4 equal spots in here. Now my delta x tells me what I have to add starting on the left side to each one to get to it. So if I add 1 to 1, I get 2. Add 1 to 2, I get 3. Add 1 to 3, I get 4. So these are my different x values. Now keep in mind that we're using the left-hand rule right now. This makes a big difference. So what we're going to say is that our approximation is the values of f of 1 plus f of 2 plus f of 3 plus f of 4, and all of this is times 1, which was our delta x value. By plugging these in of what we knew from this table, so we're just literally plugging 1 into the function 3x plus 2. That's where all of these values come from right here, the 5, the 8, 11, 14, 17. So f of 1 is 5, f of 2 is 8, f of 3 is 11, f of 4 is 14. And we're going to add all these up and multiply by 1, and we're going to get a value of 38. So our approximation for using our left-hand rule for 3x plus 2 from n equals 4 from 1 to 5 would be 38. We can also use the right-hand rule on this same exact problem. So everything on this one is the same exact as the other one, except for now we're using right-hand rule. So for the right-hand rule, we're still between 1 and 5. The only difference is the way that we write it. So now we would be f of 5 plus f of 4 plus f of 3 plus f of 2 all times our value of delta x, which is 1. So in this case, f of 5, so we would have 17 plus 14 plus 11 plus 8, which gives us 50. So we have an overestimation of this. So if we're using the left-hand rule, we're going to start from the leftmost point, and we're going to count whatever n value is. That's how many points we're going to use. So we used 1, 2, 3, and 4 on the left-hand side. On the right-hand rule, we started at 5 and then counted down 4 spots. So 5, 4, 3, 2. Now, one that is slightly different is our midpoint rule. So for our midpoint rule, we're still going to have our points 1, 2, 3, 4, and 5. Now, the only difference here is since it's a midpoint, once we created these intervals, we're going to create the subintervals that are 1.5, 2.5, 3.5, and 4.5. So by taking the midpoint of every single one of those values, we get our midpoints. These values, 1.5 through 4.5 there, are the same values that's here that will give us these values. Midpoint rule is special that we're going to use every value and not just 4. In this case, we will use 4 because we're going to have 4 subintervals, but every midpoint we're going to use. So by doing that, we're going to have f of 1.5 plus f of 2.5 plus f of 3.5 plus f of 4.5. We're going to take and we're going to multiply this by our delta x, which is just 1. So that's where we get these 6.5 plus 9.5 plus 12.5 plus 15.5, which gives us a value of 44. So notice we had 38 for our leftmost, which was an under, 50, which was our right, which was an over, and 44 was our accurate. So if we want to see and compare this, the exact value, which we could calculate in the next section here, would be f of x equals 3x plus 2, which is 48. So our exact is 48. We had our underestimate at 38. We had our overestimate at 50. Our most accurate was 44. Think about Price is Right rules. You're trying to get the closest that you can to it without going over it. So 44 would be our most accurate approximation.